All right, I think we can get started. Hello everyone and welcome to the next in Sutron's series of best practice webinars. Today we will be covering telemetry options as they relate to environmental monitoring. If you have any questions during the presentation, please feel free to type them into the chat box. I'll be posing your questions to the panelists at the end of the presentation. On our panel today, we have Weston Winegar and John Humphreys. Weston is Sutron's Business Development Manager for the West Central States, and John handles customer service and projects covered by our Integrated Systems Division. Both have extensive careers in environmental monitoring and are great resources for this topic. Their contact details will also be available at the end of the presentation. And with that, I'll hand the presentation over to Weston.
Thank you, Joe. I'm Weston Winegar. As Joe mentioned, I am the Business Development Manager for the Western States area for Sutron. I'll be doing the main presentation, and John Humphreys will be answering questions afterwards. John has over 30 years in this industry, and in my opinion is probably one of the best field service reps in the industry. But before we started, I wanted to take just a brief moment to talk a little bit about the company history of Sutron, because we have a great history and it really relates to this presentation in that Sutron was founded by some USGS employees that saw the future in data collection, in real-time data collection and telemetry. At that time, data was collected manually and taken back to the office for evaluation, and so they started building data loggers and transmitters. Today, our flagship products are our data loggers and our transmitters, and we're committed as a company to quality data in the hydrological, meteorological, and oceanic industries. Some of the topics that we're going to talk about today, as I mentioned, the topic of this presentation is telemetry. We want to cover all your options. If you're looking at moving data from point A to point B, what are your options? We'll be covering satellites, cellular, line-of-sight radios, telephone, and direct connections. A note, this is meant to be an introduction of the technologies that are out there and not an extensive listing or a training on any of these technologies. And another note, we are Sutron employees, and Sutron is sponsoring this, so I want it to be an introduction of the technologies, but we will also be talking about Sutron equipment as examples of equipment that you can use for these technologies. We'll be talking about the devices of the equipment, the advantages and disadvantages of each type, where and how to best use each type, and of course the hardware and the software to collect the data. I want to spend a little bit of time at the end of the presentation on software. Now that you've built a network, a data collection network, what are the options for collecting that data? And as Joe mentioned, at the end of the presentation, we're going to reserve some time to answer questions. So there's a chat box so you're able to request questions. So feel free, if you have any questions, to answer them. And at the end of the presentation, you'll also have John and myself's contact information. So if you submit a question that we don't have time for or don't get to, feel free to contact us directly, and we'll do our best at getting you an answer. So before I jump into satellites, one of the things I wanted to spend a few moments on is talking about the different type of satellites that are available for data collection. Most of the meteorological systems are geosynchronous satellite systems, meaning that they're in orbits around 22,000 miles above the equator and follow a geographic location on the Earth. And so these are high Earth orbiting satellites that follow one particular location, so they can take real-time data and consistent data of a particular area of the Earth. The GOES satellite system that we'll talk about later, and most of the meteorological satellite systems that countries own are geosynchronous satellite systems. And then the next graphic, I asked my daughter to produce a graphic because I couldn't find one of geosynchronous versus low Earth orbiting satellites. And I like this, so I decided to use it. Most little girls are drawing pictures of puppies and unicorns, and my daughter draws low Earth orbit satellites and geosynchronous satellite systems. So a low Earth orbit satellite system is a satellite system that is orbiting anywhere from 99 to 1,200 miles. And you compare that to a geosynchronous, which is 22,000 miles out there. These low Earth orbiting satellite systems circle the Earth anywhere from 88 to 127 minutes. So if you think of 60 minutes in an hour, these systems, these satellites are orbiting the Earth in a little under 2 hours. Iridium is an example, and we'll talk more about Iridium later, is another example of a low Earth orbiting satellite system. The principle behind Iridium is there's 66 satellites, and at any point in time, there's one satellite on the horizon that you can use for data communication. So, jumping into the geostationary satellite systems internationally, and I just wanted to touch on these, and we'll talk a little bit more about them later. And again, these are only a few of the different satellite systems available, a few of the main ones. It's not an extensive list, but EMUSAT is the European Organization for Exploration of Meteorological Satellites. It's a convention agreed to by 30 European member states that funds and that provides the data for those countries. INSAT is the Indian National Satellite System, a satellite system based out of India that's also used for broadcasting, telecommunications, and search and rescue. And then the MTSAT is the Japanese Meteorological Agency satellite system that does meteorological information in Japan. And FY2 is the Chinese satellite system. This isn't meant to be a graphical representation or a map of what the satellites cover, but I thought it was a good graphical representation of the fact that around the equator and with all the geosynchronous satellite systems from all these different countries, you have a good coverage, again, around the equator, not on the poles, but that's a different conversation, of the entire planet. And so we work closely with the University of Hawaii Sea Level Center, and they are under a mandate to try to collect data from the whole Pacific Rim. So they use a GO satellite system, but sometimes they're out of range and have to use some of these other international satellite systems. And according to them, you fill out the paperwork, and if you can provide good rationale as to why you need the data, they're fairly easy to work with and will grant you access to those systems. So the GO system, the Geostationary Operational Environmental Satellite System, is the system that most people on this call will be using. It's a system that all the government agencies use, and it's operated by NESDIS, the National Environmental Satellite Data and Information Service, which is a division of NOAA. There are two operational satellites. There's GOES East and GOES West, and they are geostationary, so they're in 22,000-mile orbits above the Earth's surface. I want to first talk about getting access to the GO system. If you are a government agency, a Bureau of Reclamation, Corps of Engineers, USGS, you automatically have access to that system, and it's a system built for you. If you're a cooperator, the first thing you need to do is submit a request from NESDIS. If you're a state agency or even a private user that wants to collect data from a location that the government might be interested in, you can submit a request from NESDIS and fill out the paperwork to get access to that system. And they're pretty good with working with you, so they're a great group to work with. And we can even walk you through that if you need some instruction on how to do it. So getting access to the system, this is a screenshot from SatLink Communicator, which is a software program we use to program our SatLink, our GOES transmitters. And I put this in here just to show that the first thing you need to do when setting up a transmitter, a geostationary transmitter, is select the satellite system that you're using. And I do this because I talked about all those international satellites. And as you look at this pull-down menu, a lot of those international satellites are listed here. The hardware, as far as the transmitters go, is the same for all the geostationary satellites. And our SatLink 2 transmitters have been certified for all these geostationary satellite systems. You need to select the satellite you need, and according to what system you're using, there's also other parameters that you have to configure. We select GOES 300 satellite system because that is the system that NESDIS will assign you to once you get permission to use it. Setting up the satellite AD, the next thing that you will need if you get permission to use that system is a satellite ID, which is a unique number that will identify you both with the satellite system and with NESDIS. So you input your satellite ID into the system, and then you will also be issued a time slot. The GOES satellite system isn't like the internet in that you can just send information anytime you want to. The way that that system is set up is there's time slots, and when you use the system, you'll be able to, you'll be assigned a time slot, and that time slot is the time slot you will use. You will only be able to transmit data to that system in that time slot. The equipment, elements of a GOES station. The first thing that you're going to need, of course, is a transmitter. I put on this graph a GOES logger transmitter. Our first generation of GOES transmitters was just a transmitter, and you needed some type of a logger to collect the data and put the data in a format that it could be transmitted. The current version of our SatLink transmitter incorporates a data logger into the transmitter. So it's not just a transmitter, it's a GOES logger transmitter. So it's really two pieces of equipment in one. A Yagi antenna with a cable. The Yagi antenna is a 43-inch directional antenna, meaning that when you install this Yagi antenna, it needs to be pointing at the geostationary satellite that you're assigned to. There are different programs out there that will help you determine the angle and direction that the Yagi needs to be installed. And the SatLink communicator, the program that I talked about previously, there's also utility in there that if you input your latitude and longitude, it will tell you the direction that you need to point your antenna. A power system. Most of these systems are incredibly remote and don't have local power, so you're going to need a battery, a solar panel, and a solar regulator to take the voltage from the solar panel and charge the battery. And of course your sensors. We build the logger in these sensors to handle almost any type of sensor that's out there. And so it will handle a variety of sensors, and you need to program those sensors into your logger. And once you do that, you have a working system. Advantages and disadvantages of geostationary systems, most notably the GOES system. Like I said, that's the system that most people will use, but this really applies to all the geostationary systems. Advantages, it's a low annual cost. If you're a government entity, of course it's owned by the government, so there's really no cost. And if you're a cooperator, it's usually a real reasonable cost. It's geostationary, so it follows the Earth's surface. You always will know where it is because it's in the same place in the heavens. It's available anywhere in the coverage area. So even the remote locations, if it's North or South America, you'll have access to the GOES system. Very reliable. It's a robust system, and it's generally low power. Since it only transmits in a window, the system's able to conserve energy and almost put itself to sleep while it's waiting to transmit. And it supports real-time alarming. I talked about the windows. You're assigned a window, but the GOES system also supports event-driven transmissions. So these systems, if you have parameters that are breached and you want to send an event-driven transmission, it will send random transmissions. There are sometimes problems with those because it might have collisions with other people's transmissions that are scheduled, but you can send event-driven transmissions on the GOES system. Disadvantages, higher hardware costs. The SatLink transmitters, in compared to like a cell transmission system, a cellular or Iridium system, the Yagi antennas are a little more and the transmitters are more. And then approval. You do need NESDIS approval in order to use this system, and the data is public. In the GOES system, NESDIS gives access to the public to all the information that's in that system as far as the data that's collected. And one of the big disadvantages is the GOES system is transmit only. You don't have two-way communication. You can't request data. You can't send updates. If you need data from or need to update parameters on the station, you need to go out to the station to do that physically. And then the higher data acquisition costs. The NESDIS data is public, but if you want to collect your own data, what's required is to build directly from GOES, you need to build a satellite receive station or buy a big satellite dish to do it. And I'll talk a little bit about that later. Project profiles. For each one of these, I wanted to talk a little bit about a project that uses that type of a system. The USGS, Corps of Engineers, Bureau of Reclamation, and National Weather Service are the biggest users of the GOES system. So that would have been easy. The state of Colorado I'm pretty passionate about because of the commitment they've made to the GOES system. In the early 80s, the state of Colorado determined there was a need for timely, accurate water data. So they established a committee that went out and determined that the GOES system would be the best system to use. They were able to get the funds approved of close to $2 million, and they purchased a total of 150 systems, satellite systems. Passed acceptance testing, the system was dedicated, and in 1986, it was selected as one of the 10 outstanding national engineering achievements for 1985. So it was a big deal. I like these pictures in that these were some of the first stations, which were the yellow bricks. We started manufacturing of these in 1979, and I often see these as I visit the GS offices and glass enclosures of museums in the front office. But I've been told that there are even some yellow bricks that are still operational. Well, not that they're out in the field, but you put power to them and they still work. So it was a great product for us, and it was our first generation of GOES transmitter. So today, Colorado has over 520 GOES stations that are installed and monitored by the state of Colorado. They work closely with the USGS that has another 380 stations. So an extensive network of GOES stations throughout the state of Colorado. That's a great project. So you don't want to use the GOES systems. Maybe you need two-way communications. Maybe you need to keep your data private. Maybe you need to work with something in the middle of nowhere. There's another satellite system you can use, which is the Iridium satellite system. And I like the whole Iridium system just because it has such a great story. The Iridium system was launched in the early 90s, and the first phone call was made by Al Gore in 1998. And then 9 months later, they filed for bankruptcy. Motorola had funded the system, and their business model was based on the fact that people would buy a phone for $3,000 and then pay $3 to $7 a minute for a phone that worked anywhere on the planet but had very poor service. And so the business model didn't work out. They had 88 satellites originally, and there's, as I mentioned, the whole system is based on 66 satellites. With that graphic there, you can see the 66 satellites and the orbits they were in, there would be coverage everywhere on the planet. Well, they were within weeks of loading the suicide software to destroy the system and burn the satellites up. And the Department of Defense and some private industry recognized this as their most robust, low Earth orbiting private satellite system that existed. So they stepped in and helped to keep the system. They found some financiers. Iridium is now the name of the company that owns it and manages it. And it is still, 30 years later, the most robust and powerful satellite network that's available. It was built for phones, around 32-bit processors. But what we have done in this industry is we use this for SBD, or short burst data, which Iridium loved because it created a whole new market for the Iridium system. It was more economical for the users, and it also made, there were more customers per bandwidth, so they were able to get more customers onto the system. So, and I'll talk a little bit about that later. In order to access the Iridium system, the equipment you're going to need, if you have a data logger that's collecting data and putting it into a format that you can transmit it, all you need is an Iridium modem. So there's an Iridium modem listed. What we did is we took an Iridium modem and we built it into a data logger. So if you have multiple parameters that you need to measure, you can use the Iridium Link, which is a product that can measure up to 16 measurements and has a built-in Iridium modem. The antenna, I put a picture of that there just to show that it's an omnidirectional antenna versus a Yagi, which is a directional antenna. The antenna is omnidirectional, meaning it will find a satellite, as there's one somewhere on the horizon, and transmit or receive data from that satellite. And I included this picture of installations because I just wanted to show that in this NEMA enclosure, and we offer a product that has an Iridium Link and a NEMA enclosure, but there's a NEMA enclosure with a battery, a solar regulator, and an antenna all in that enclosure. You throw a solar panel onto that, and that is a complete Iridium transmit and receive station. And so it's very low profile, very easily installed, and it's a great product if you need to transmit data in a real remote location. Advantages and disadvantages to the Iridium system. Advantage, it's available anywhere on the planet, and it's got two-way communication. That's a big advantage in that if you have a flood warning system or a tsunami warning system, you don't necessarily need to get data every hour. You just are interested if it's raining or not. And if it's not raining, you can do daily health checks. But if it starts raining, or if it starts raining hard, or in the example of a tsunami, if there's a seismic event, you want to be able to turn the system on and get real-time data. And so two-way communication becomes an issue. And if you want to send updates or if you want to request data, you don't want to have to go to the site. So two-way communication is a really big advantage. And then for SBD, for short burst data, it's very reasonably priced. To activate a typical Iridium system, you're looking at about $108, and then $25 per month to start. $25 per month gives you about 12 kilobytes worth of data. So if you're just taking water level measurement is about 5 bits of data. And so daily water level measurements or even hourly would probably fall within that range. If you're doing something more, well, I'll talk a little bit later about getting quotes on how much data you're using. And then relatively low power. Since you're only transmitting 400 miles up into the air, it's a fairly low power system compared to some other types of systems. And then the disadvantage, for large amounts of data, if you're sending pictures or big data with water quality systems, the prices do get expensive because, again, you're paying for how much data you send. A quick project profile, and I love this project profile just because it's so unique. The Kingdom of Bhutan, they were having problems with glacier lake outburst floods, which were basically these natural reservoirs that were created by glaciers that would, in the springtime, as things began to thaw, would break, and they would come down and really devastate the village. In 1994, a glacier lake outburst flood, say that 5 times fast, claimed 22 lives and caused some serious infrastructure damage. And so the Kingdom of Bhutan recognized that we need some type of a system to warn some of these villages to take safety. So they put out a bid, we won the bid, and we determined Iridium to be the best alternative to the remote locations that they wanted to install these. Some of these locations we actually had to use yaks to haul our equipment into the mountains. So we installed the system. It's a great system and includes about 23 stations that include sirens for the small communities and a control center. And as you can see, they use the Iridium satellite system to get data from the stations. Then that Iridium, through the Iridium gateway, provides that data to their server in Bhutan, where they can monitor the data, they can set up alarms, view the alarms if they take place. And then as far as administration and support goes, we can, from our office in Sterling, Virginia, also see the same data and log into their system and help them if they're having any issues. So it's a great system and in a very remote location and a great example of an Iridium type system. So say you don't want to use a satellite system. Say you want to build a network in either a metropolitan or not that remote where you have cellular access and you want to use cellular technology. We can use the data bandwidth of cell networks in that we're just using the same bandwidth that you send texts with. The technologies are CDMA that Verizon uses for code division, multiple access, GSM, GPRS, which is General Packet Radio Service that AT&T and T-Mobile use, and then HSPA, which is high-speed packet data, which is equivalent to 3G, whereas CDMA and GPRS are equivalent to 2G systems. For each of these systems, we've developed linked products. So, well, before I go into that, I want to talk a little bit about using cellular IP modems, GPRS or CDMA modems. So say you have a serial device and you want to collect data from that device. You can collect it to an IP serial modem as long as you have cell access at the location. With this IP serial modem, you now have an IP address that over the internet you can connect serially to that device to download the data. And so you now have a remote device that is accessible over the internet through a cell network. Well, if you have 2 or 3 devices, it becomes a little more complex because you don't want 2 or 3 serial modems. And that's why we have taken these modems, GPRS, CDMA, and HPSA modems, and built them into data loggers. So now you have a data logger that can use a cellular network to transmit data. I included the graphic in the lower right-hand corner there of antennas just to show that there's a lot of antennas available. I've done the installation on one of these systems, and I put the power to it before I hooked up the antenna, and without the antenna, it started transmitting. So you don't need much of antenna, especially if you have a lot of bars. But the point I wanted to make was, if you are there with your cell phone at the location you want to send data, and only have 1 or 2 bars, there are high gain antennas that are available that are much of a higher gain than your cell phone is. So even with a very low access and a high gain antenna, it's very likely that you'll be able to transmit data from that location. And in the center there, on that 2-inch pole, is mounted another one of our products, which is a self-contained CDMA link that has a modem, a data logger, a battery, a solar regulator, and an antenna, all in that small NEMA enclosure that you can mount onto a 2-inch pole, put a solar panel on, and you have a really portable, really easy to use and install telemetry system that you can hook up to sensors. Advantages and disadvantages of cellular communications. It's available anywhere with cell access. It's 2-way communication that we already talked about. And it's very reasonably priced, $60 for activation, and plans start at about $10 per month. And for those of you that have teenage daughters, you know that every month you have no idea what your bill is going to be. Not the case here. 1 meg of data is for the $10 per month. But if you have a system where you're, and this is what I was going to talk about with Iridium, the same applies to Iridium. Say you have a system where you know you're going to collect water level, and you have a temperature measurement, and you have a maybe a water quality, a pH measurement, and you know exactly what you're going to measure. You can talk to one of our technicians, and we can figure out exactly how much data you're going to need to pay every month. And so it's not that case when you have something like a flood warning system, because you don't know how much you're going to measure. But if just a data collection system, it becomes really easy to create a budget on how much data you're going to need. And of course, the disadvantage is it's not available if cell service is not available, of course. So now jumping from cellular communication to radios. Radios, if you don't want to send data over the sky, if you want to own your own system, you can build your own radio network. I wanted to briefly go over some of the technologies that are out there for radio networks. The first being spread spectrum radios. They go quite a long distance, and they go 5 to 10 miles. It's license-free, meaning that you don't need a FCC license to use it. And it's a real high-quality serial connection you can make from point A to point B, versus the UHF, VHF radio, which requires an FCC license. I didn't write that there, but these radios require FCC licenses, but they're also very high, ultra-high frequency and very high frequency radios that will transmit data anywhere from 20 to 40 miles. So they can go very long ranges, but again, they are FCC licensed. And so these radios will create a serial connection. If you need to pass more data back and forth, or if you need some type of an Ethernet connection, there's line-of-sight MDS Ethernet radios that can do that for you, that can create an Ethernet type connection over very long distances. And then I wanted to just touch on radio voice modules with King radios. We did a system where they had a King radio system built with repeaters and transmitters, and they wanted to use that same system that they use for voice to transmit data. So we adapted our voice modem modules to work to send data over the same system that they were using for their King radios. So, project profile. I wanted to talk about a project or a community that was using radios to great benefit. Lower Colorado Water Authority, which is a great system and a great community, headquartered in Austin, Texas. Lower Colorado Water Authority manages a 22,000 square mile area, and they administer over 300 gauges. Some of these areas have some of the worst flash flood problems in the nation. And so they built a system that's a 900 megahertz radio tower, and it's a trunked radio system, meaning that they use a two-way radio system that allows the sharing of relatively few radio frequency channels among a large group of users. And I wanted to talk about LCRA system because they're now transitioning over to even a better system called the Open Sky system. But the premise of their system is they have this radio system that they built, meaning that if you're considering building a radio system, you have to consider its line of sight. So if you have mountains, if you have buildings, you need to build repeater stations that will collect the signal and get it over these areas. But once you've built this backbone of repeaters and receivers and transmitters, you have this robust system. So they build this system that they can use for their telemetry, so that for their data collection. But they also now have a system that they can use for emergency responders. So the same system they're using for telemetry, they can use for police and for ambulance and for fire. And so there's all these other uses that you can use a radio system for once you've built a really robust radio system. So advantages and disadvantages of a radio system. Advantages is that you have total control over all aspects of your network. The network is yours, and it's a private network. You don't have to share your data, and you control every aspect of it. You have two-way communication, so you can request data. You have unlimited bandwidth as far as receiving data, so you can get real-time data, or you can make changes to your stations as far as their parameters. And there's, of course, no fees after installation. You own the system, you own the bandwidth, and you don't have annual fees that you have to pay. The disadvantage is it's heavy maintenance. You're building the system yourself, so these systems require quite a bit to set up and to maintain. So if you don't have staff to do that, you might want to reconsider. And then another line of disadvantages, just a reminder, these are line of sight systems, and so you need a good line of sight from the receiver to the transmitter in order for it to work. And in fact, if you're considering these types of systems, we recommend you do first a paper path study where you get a geographical map of your area to see if it's going to work. And if it works on a paper path study, we recommend a radio path study, which involves two technicians actually going on site with the types of radios you're going to use to make sure you can make a connection between point A and point B. And so there are some geography issues or geographic issues that you need to consider when considering these radio systems. And I wanted to talk a little bit about one of our products, the SDI-Link. SDI-12 is a sensor protocol that's used in the sensor industry. And it's a great protocol to use if you're using sensors in that there's a command set with SDI-12. So you can send a sensor request. For example, you can ask a sensor to send a measurement, and it will take a measurement and then send it back to you. Or you can say, take your measurements over this time period and average them and send it back. And it'll take measurements, average them, and send them back. So it's a command set that sensors use that's used in this industry quite a bit. Well, we built an SDI-Link, which has the ability to, say you have a basin that's a 1 square mile basin, and you want to collect data from several different areas in this basin. You don't want to set up those sites at each one of the locations. You don't want to have an Iridium modem at each one of the locations. So you could use a master SDI-Link, and at each of the sensors use a slave SDI-Link. All these slaves will collect the data, transfer it to the master, and from the master you can send it up to the GO satellite system. So it's a great way to build a network without having as much expense as it would to have stations everywhere you need it in the network. And another device that works similarly is the Modbus-Link, in that if you have Modbus devices, you can hook them up to the Modbus-Link, and it's a multi-hop mesh network. So what it'll do is find a close Modbus link and transfer the data until it finally finds the data logger. So it will build a mesh network from wherever you install these stations. And then I wanted to talk just briefly about just direct connections. If you want to build a data network, you can also use just the standard old-fashioned direct connections. A direct leased line, when you're collecting meteorological data, sometimes it's very critical data in that if it's a warning system, you want warnings that floods are coming and you don't want to rely on a poor internet connection. So a leased line is basically point A to point B that you want a connection. You can buy a line that is almost like a physical line, uncontended space through the cloud over an Ethernet connection. Serial communication is the most standard way of connecting devices. It's serially, and of course, Ethernet. Ethernet, you can build a network with data loggers the same way that you can build a network with computers. Most of our data loggers now have Ethernet ports, so you can assign IP addresses to the data loggers, hook them to an Ethernet network, and it'll build a network of data just like you can build a network of computers. And I love the graphic. Thank you, John Humphreys. Voice modems, they've been around for a long time, just like old Barney Fife. But voice modems are the old way, the traditional way we've used to connect or build networks out of data networks, and they're still viable today. If you want to build a network by just connecting voice modems, that's still available. So I think I've touched on, at least touched on and did an overview on all the different elements and all the different scenarios of data collection. But what I wanted to spend just a couple slides on data collection, or the software that you use to collect and evaluate your data. So you built a network, whether it be a radio network, or an Iridium network, or a GOES network, or a cell network, and now you have to sit back in the office and say, boy, I got this network. Now what am I going to do? I got to figure out a way to collect this data. There are three ways I wanted to talk about. One is a web or a cloud-based system to where you have somebody else collect all the data, do all the work to get the data to you, and all you want to do is log into the website and observe your data. Two is a server-based. I'm going to talk about XConnect and Tempest. Basically, you want to collect your data yourself. You want a self-contained system. You want to have a server at your office that has your data, so you don't have to rely upon anybody else. And then computer-based. Computer-based is, I don't want to build a system. All I'm interested in is the data, and I'm not even really interested in analyzing it. I just want to collect the data off the equipment. So the first system, there are systems out there that you can log into a website, say whether you're a rancher that has 2 stations or an irrigation district that has 100 stations. You can have somebody else collect the data for you. You can log in the website and view your data. Sutron Win is a product that we have. Sutron Win is a product that will collect your data, we will host your data, and we build a platform in which you can get in. You log into Sutron Win with a username and password, and it will display a map of all your stations. And from that map, you can either look at the real-time data, you can look at historical data, you can build reports, you can set up alerts and alarms, and all you are doing this from is a login. So everything else is done on the back end. And I have this slide only because it's very complicated. And I wanted to point out that the way that Sutron Win works, if you have, say you do have your irrigation district and you have 100 stations. Some of those stations are Iridium, some are cellular, some you're plugging with radios, and maybe you even have some U.S. Geological Survey stations on your property, and you're interested in that information. Well, Sutron Win can be set up to collect all that data, because as the water user, you're not really interested in what type of telemetry is being used. You're just interested in the data. And so Sutron Win will collect all that data regardless of the source and put it in a similar formats so that all your data looks the same. And all your data shows up, and as you do reports, it does the reports on the data, not where the data came from, as long as it's all good data. So you're only interested in the data and that it's good data, and everything else is on the back end, and we work everything as far as the data collection goes. So say that you're a state agency or you're a Corps of Engineers office and you want to collect your own data. You want your own satellite dish and you want to pull the data off of the GOES system yourself. You can get a direct readout ground station or an LRIT and LRGS, which are smaller versions of that, that will actually pull the data directly from the GOES satellite system and populate a database. Tempest is a toolkit that is used to pull GOES data in, decode it so it's in a format that's understandable and you can do reports out of and populate a database with that can be used with a DRGS system. And then XConnect is a product that we offer that is a server-based product that will pull in data from a lot of different sources and gives you a front end where you can do reports and then do evaluations or even, again, populate a database with the data. So it's these are all products that will collect the data for you and give you tools to evaluate and disseminate the data. And the last thing I'm going to talk about as far as data collection software and systems is computer-based IP data collection. If you have a serial device and you just want to log into that device and pull the data off into a CSV format, you can use Hyperterminal. We talked about a serial IP modem that's connected to a serial device. With the IP address, you can make a Hyperterminal session, log in, and download the data. And then AutoPoll is a simple program we developed just to solve the needs of people that really just needed a simple solution. It's a program that you can program the IP address into along with time frames. Say you want to download the data from 5 or 6 devices once a day. You put the IP addresses in a time frame, and every day it will download the data and create a CSV or an Excel spreadsheet type document that has all your data from your devices from the very simplest level. So I started complex and went simple. Maybe I should have started simple and went complex. But in conclusion, what I wanted to talk about is we talked about a lot of information. It's a lot of information that many people on this call are probably familiar with. But I wanted to try to analyze all this information and all this knowledge we now have because, again, most people on this call probably already have a system. But taking a step back, if you are somebody that is saying, okay, I need to build a data collection system, what do I need to consider and which system should I go with? We get that question a lot. People that need to collect data, how are they going to do it? And so I tried to build this decision tree to answer some of the questions that you might have. And so I wanted to go through it piece by piece. It's fairly confusing like this. This next slide, I tried to gray out the areas I'm not talking about. You need to collect data. The site is not remote, and so is the site remote? The answer is no. You can use Ethernet or direct phone lines. When I say direct phone lines, that's confusing nowadays because is your cell phone a direct phone line? No, it's not. So a direct phone line is something that's plugged into your wall, meaning that you can't be remote to use it. You can use that, or you can build an Ethernet network. So as I mentioned, most of our data loggers now have Ethernet ports you can plug into to build a network of data collection systems. The next one, do you have a good line of sight? If you need to collect data, you have a good line of sight, you can build your own radio network. So you can build a radio network with with data loggers and radios that will collect the data and bring it back to your site. And you can also use that wirelessly. You can use wireless Ethernet modems now if you can get a wireless signal. It's not you can't go as far as with the radios, but there's ways that you can do networks where it's a self-contained network and you don't need to rely on any other option for telemetry. Is the site remote, and is it a U.S. Geological Survey, National Weather Service, Bureau of Reclamation, or Army Corps of Engineers, or a government cooperative like a state agency, or a private user that is just measuring in a location that would be of interest to the USGS? If that's yes, then you can use the GOES Geosynchronous Satellite System. You just need to submit the paperwork and get approval by NSDIS. Is there cell access at the site? Is it remote and there is cell access? Then, of course, you can use one of the cell technologies to transmit data, GPRS, CDMA, or HSPA. And, of course, last but not least, if there is not cell access and it's very remote, Iridium is also a really good solution. And this next slide, I didn't know how to put this in there without making it really complicated, but I just wanted to answer this question because maybe you don't need two-way communication. Maybe you're just monitoring for historical water levels, and you can use the GOES system to do that. But if you do need two-way communication, All the other systems offer that. Radios and spread spectrum, if you own the network, you can even get real-time and open up your bandwidth to do that. Cell modems, you have two-way communication, you can request data. Iridium also, and then Ethernet, of course. As much as even an Ethernet network will give you, you can have real-time communication, two-way with those systems. So that concludes my portion, and I wanted to thank everybody for joining in. I hope everybody found this interesting. Like I said, it wasn't meant to be extensive, but I tried to touch every area and use what we have found to be the best option for every area that you will face when you're considering putting together a network. And so at this point, I'm going to turn the time back over to Joe and John for the question and answer period.
Yes, thank you, Weston. We've been collecting some questions, and our first question comes from Scott Bradford. Why are Iridium and Beacon so great with data transmission, yet so unreliable with sat phones?
Well, that's a pretty good question, Scott. I've actually been asked that quite a number of times. The main thing, just like a cellular phone, you have to be connected to a cell in order to keep the phone active. The same thing happens with Iridium. If you're in a nice open area and you've got view of, say, a number of the satellites, you're probably not going to lose the connection. However, if you're in a ravine or something, there may only be one or two satellites available to you, and if you lose that connection, of course, the phone drops out. The good thing is with short burst data modems, however, is that we really don't suffer from that same handicap. The data transmission happens so fast that you are just not going to drop the call. We're shooting very fast baud rates. It's usually milliseconds to just a couple of seconds to get the data packet out. So, good question, though.
Okay. Cindy asks, what would be the best telemetry type for moving targets like ships?
It's not necessarily the telemetry type that's the best. It's going to be more or less just making sure you're transmitting with an omnidirectional type of antenna. There's GOES systems out in the ocean that are on buoys, and so we don't use those Yagi type antennas. We transmit higher power through omnidirectional antennas. So it really depends on what's available to you and what meets your needs as far as the telemetry options, and then of course, just if you're moving around, you just need the omnidirectional antenna.
Okay. Next question is from Philip. You mentioned something about Tempest decoding. Why exactly does my data need to be decoded before I can use it?
Tempest, typically we're decoding GOES messages with Tempest. We can decode most any message, however, it's primarily used for GOES decoding. And because you have such a short window with GOES, you've got usually about a 10-second window, and GOES is fairly slow baud rates. So you've got a fixed amount of data you can get in there. So what we do is we will compact the message, send a pseudo-binary message, which is unreadable to the normal person. You have to get in there and get those characters all decoded, and nothing is time-stamped because we're trying to save space and things. So it's a little bit of work getting the message unraveled after it's been coded up like that.
Okay, we've got a question that just came in from John Ramirez. What is the best transmission system for warning signals?
That's a very good question. Warning signals implies, alarms and everything, and you want things to be available when the alarm occurs. Cell works well. However, if there's an event, you've got a lot of people using the network and stuff, so there's limitations there. Quite frankly, for alarms, I've always found that Iridium works very well. You can go modem to modem with Iridium, which means you can have the event happen a number of miles away and send the alarm through the modems, through the satellite to the other modem to trigger a relay or something like that. We've done this before in a mine area where we're taking samples. We're triggering a sampler many miles away from the actual point of measurement. So I think Iridium works very well in this regard.
Okay. Nitin asks, can you go into a little bit more detail about real-time alarms via GO satellite? If I only have a small transmission window, how can I be assured that I'll know about events as they happen?
That's a very good question, actually. GOES, over the years, they used to be based on a 4-hour window. Now they've cut it down to a 1-hour window. So, you know, for the most part, your standard self-time transmissions will satisfy most of the needs out there. However, you may want more real-time notification. So they do support a random channel, and so it's more short burst data. It's usually just a couple of values, not the longer messages that are sent in the self-time. And you can set the platforms up such that when the unit goes into alarm, it immediately generates the transmission. It does not have to wait for the next available window. So there are ways that GOES has accommodated the real-time environment.
Okay. Samir asks, can an Iridium antenna be used to work with any other type of satellite communication?
Probably not. The Iridium it's a fixed frequency. It's about 1.6 gigahertz, and antennas are primarily built. They're a tuned piece of metal most generally, and that's why you get such varied sizes on them, and because they're tuned to different frequencies. So if it's been tuned to 1.6 gig, then chances are it's going to only work at the 1.6.
All right. Mike asks, is it possible / practical to use a serial cell modem to provide real-time telemetry?
A serial cell modem. There are a number of modems available, and whether they be serial or like an Ethernet type of a connection to the data logger, most generally what we do is the modems themselves are given a fixed IP address, so they can be contacted via some cloud-based polling software or what have you.
Okay. Victor asks, if direct line of sight doesn't affect cellular communications, why does it become more tricky in mountainous or forested areas?
Well, that's kind of a misstatement in the sense that direct line of sight does affect cell systems. I live in Idaho, and I get dropped quite a bit. So it's primarily a geographical thing. You know, they'll have more cell towers out there than a typical UHF VHF radio system will have repeaters. If you're in a very mountainous area, the main thing with radios is you need to have line of sight, and if you don't between the two stations, you need to have a point in between that can be seen by both sides. So line of sight is critical for both technologies.
Vadim asks, how can remote stations function if sunlight is unreliable?
Oh, good question. I deal with people in Alaska quite often. There's a couple of ways you can deal with this. The obvious answer is get a larger solar panel, but if that's really not feasible, there are other ways of charging batteries. There's wind chargers, wind generators, and quite a number of times they use propane chargers. I have actually not had too much experience with them, but folks that we have worked with over the years have used them in the past.
Okay, next question from another Mike. Best option for deep canyons?
Deep canyons. Generally, it's a satellite-based system because, again, you generally were going to have line of sight between the satellites and and your ground station. However, GOES, because of the fixed satellite, there are times when you might have the mountain right in your way. There's ways with GOES you'd have to move the actual transmit antenna to some other location that can see the satellite. There's ways of doing that using short-haul modems and things like this. Or Iridium is quite frankly a very viable solution, because you're always going to have one of those satellites in view. Latencies are very minimal. So Iridium and or GOES be viable.
All right, thanks, John. I think we'll wrap it up there. There's still some pending questions, and we'll be sure to follow up with any inquiries by email after this presentation. If we weren't able to answer one of your questions, or if you want more information, please feel free to contact John or Weston using the details on this screen. And yeah, stay tuned for our next webinar. It's going to be covering station installations. Again, thank you for joining us today, and hope you have a good day.